yet, but you should be able to see it now soon.
Yes.
Okay, good.
Okay. Yeah. Okay, then it's 2:32. I suppose we can start. I hope. I don't know. I think that Massimo is there for the streaming. So let's start. Good afternoon, everybody. Thanks, Ian, for accepting our invitation for this enough Observatory Abruzzo colloquium of today. Let me introduce you to our small community. Ian is a full professor at the Gran Sasso Science Institute of L'Aquila. His research focuses on new gravitational wave detector technologies and on the analysis of gravitational wave signals and on their sources. Ian started his career as a PhD student at the University of Hannover, where he got his PhD in 2006. And then he had quite a few experiences as a postdoc at leading scientific institutes like Caltech, University of Minnesota, MPI for gravitational physics, INFN, and then until 2017 he joined the Gran Sasso Science Institute. Among the others, Ian is member of the Virgo collaboration, is also a member of the Einstein Telescope Steering Committee, and finally he is also coordinator of a collaboration on the Lunar Gravitational-Wave Antenna, which is the subject of his colloquium today. The title of Ian's talk is the Lunar Gravitational-Wave Antenna, opening the decihertz band to gravitational wave detection. Thanks, Ian, again for joining us today, for giving us the presentation, although remotely. Now I give you the microphone. I ask everybody else to mute their mic. And again, I will let you know 5 minutes in advance of the 45.
Thank you very much, Michele, for the introduction, and thank you for the invitation. For me, it's a great pleasure, especially since ENAF generally and your part specifically plays really important role for the Lunar Gravitational-Wave Antenna. So, you know, the science case development especially, but also other parts of the project are really driven by contributions from ENAF. So I think this is, by the way, I think the first presentation that I give to an ENAF group. So I think that there's going to be more, but this is, yeah, for me a great pleasure. So let me say a bit about the title first of all. So opening the decihertz band to gravitational wave detection. We have proposed this project, the specific technological concept, let's say, only a year ago, and we have been thinking since then about the science, and it has developed over time. So in the last 2 years, more or less, and what we understand today is that there is a very specific opportunity in general to lunar gravitational wave detection, and lunar gravitational wave antenna is one of the proposed concepts, which is to access the decihertz band for gravitational wave observations. Now, it's something that was left over because there's LISA at low frequencies in space as a satellite mission. There are the ground-based detectors, but somehow all of this is leaving a gap in between the decihertz band, and it's not by chance. It actually is so because it is technologically extremely challenging to propose a detector that can see something in that band. So it is a coincidence of nature, if you want, that we are not able to propose technologies, or so far we have not been able to propose really feasible technologies to access that band. But I hope that I can convince you that the lunar gravitational wave antenna might be a first such concept. So here is what we would like to see when a gravitational wave passes the moon. then it will produce elastic deformations, and it will produce essentially quadrupolar vibration modes of the moon, excite them, and there are certain frequencies where this excitation will be resonantly amplified. There are other frequencies where it will not be resonantly amplified. But in essence, all you have to do in the end is really place some seismic sensor on the surface and try to monitor this vibration. That's basically it. And that concept itself has been exploited in the resonant-bar detectors that you might have heard of, which played an important role in gravitational wave detection history. Italy was very important in that field. It never led to gravitational wave detection, but it was a really it was a technological concept that came very close to a detection until the laser interferometers really took over. So that kind of idea, we are coming back to it now with the lunar gravitational wave detection. Okay, so just one word. I mean, we are entering a little bit into details, but this this simple vibrational mode is not exactly what you will have on the moon, because that depends a little bit on the internal structure of the moon. So you have to know that structure quite well to better describe or more accurately describe the vibrational eigenmodes. If, for example, a big meteoroid was creating a crater with geological heterogeneities associated with that, then you can be sure that if you put some seismometer in that region, that it will be affected by the more local geology, let's say, around that crater. So these are the details that really matter. They are very important, but we are not yet able to model them accurately. So we are, let's say, in the process of preparing studies for that. Okay, now the idea of lunar gravitational wave detection is not new either. That was attempted by Joe Weber, who, by the way, also developed the first resonant bar detectors, and who, by the way, also developed the first laser interferometers. He is not so much known for that, but he made important contributions to laser interferometry in the 70s. And that has also, started the whole LIGO effort in the US, which in the end spilled over to Europe with Virgo and Geo 600. So he was a very influential person for the field. And he also had the idea to deploy a seismometer on the moon, which he called Lunar Surface Gravimeter. Gravimeter is just an indication that, the actual target that you're after is a gravitational signal, not a seismic signal. But this is just semantics. In the end, these instruments all work the same way. And here you can see this Lunar Surface Gravimeter connected here to a nuclear power device and some communication relay. All of this, of course, deployed by astronauts. So you can see here the footprints. And in print, before Apollo 17, there were already other deployments of seismometers, not the same concept as this one, and they work very well. And Weber kind of understood from the data of these previous deployments that the moon is an ideal location to search for gravitational waves. So he suggested that experiment. But unfortunately, there was an arithmetic error made by, within the company, Lacoste and Romberg, which was responsible for that development of that, the construction of that instrument. And it worked very well on Earth, but it didn't work on the moon. There was an error made concerning the change of gravity. A bit tragic, that story, but in any case, in hindsight, of course, we know there was no major damage, simply because that instrument would not have been sensitive enough to see gravitational waves. It might have given us a better idea maybe about certain, aspects of moonquakes and lunar internal structure, but not much more. So we didn't lose a lot. But at that time, of course, it was seen as a major failure of the mission. So now, before we come back to the moon, I want to go through a series of, a series of development that happened. So it turns out the very first attempt to detect gravitational waves ever with an experiment was done also by Weber and collaborators at Caltech with seismic strain meter on Earth. So Weber, who understood essentially all the important effects quite well at that time already, he knew that, okay, Earth must respond to gravitational waves as well. And so he thought, like, okay, what is the most sensitive seismic instrument that we have on Earth? And he figured out that this was the strain seismograph, and at in California, developed by the Caltech group. And so he hooked up with them, and they did some studies, and they knew more or less some of the frequencies of the resonances of these vibrational modes. And so on these resonances, he was starting to look for signals that he could associate with gravitational wave events. Now they did studies, and they set upper limits is in the end on some Riemann tensor spectrum. At that time, this is what they used. Today, we are identifying this quantity here more or less with what we call gravitational wave strain. So there are some time derivatives associated between these two. But anyway, so this is basically what we would call the square of the gravitational wave strain with some modification. And he said upper limit. But of course, what he understood from these early measurements was that Earth is way too noisy to see gravitational waves. Nonetheless, especially with a single instrument. Later on, there was somebody called Tuman who tried to find gravitational waves by correlating the data between two instruments, or making use of these two instruments in some clever way to distinguish between a seismic background and gravitational wave signals. And so here he used, this person used two gravimeters, cryogenic gravimeters with a levitated niobium ball and squid readout. So that was already very sophisticated, and he had like one of these instruments in Stanislaus State College, also in California, and the other one, I believe it was in Berkeley, if I remember correctly. So anyway, 200-kilometer distance between them, and he actually made at some point also a claim that he saw gravitational waves, which was not true. But we had a few gravitational wave detection claims throughout history, so that he was not the only one. Still, after all of that, and that was basically the end of the story for a long time, the conclusion was you cannot really do this on Earth. In 1972, I said there was the attempt on the moon, but also that kind of failed. So now we came back to all of this in 7 years ago, and our idea was, okay, first of all, the people in the past didn't really know how to analyze data for gravitational wave searches. So we have, in the meantime, really sophisticated detection pipelines that were produced by the LIGO and Virgo collaborations. And so we also understand, of course, the role of sensitivity, of the role of a network. How do you profit from a network of sensors and all of that quite well? And there are like, methods to optimally, in the end, exploit the capacities of sensors and the network. And so at some point we thought, okay, today we not only have two gravimeters on Earth, we have several tens of gravimeters, really sensitive, more sensitive than what Tuman had in the 70s. And we thought, like, okay, now let's take all of these and make it in a good way. Let's maybe correlate that data. Let's do data selection very well. Let's do the statistics in the best possible way. And let's search for gravitational waves on Earth. Another step that we did, and which is also done for geophysical studies with these instruments, by the way, is to cancel, because some noise contribution in these sensors, the dominant noise contribution in these sensors, terrestrial noise, is the gravity perturbation produced by the atmosphere. So this is a kind of Newtonian gravity noise that you have in the data of gravimeters at these very low frequencies. We talk now about millihertz, this band here. So that noise has to be subtracted essentially from your data if possible. And people do this by using pressure sensors, because the origin of that noise is pressure fluctuations in the atmosphere. And if you have sensors to monitor these pressure fluctuations, then you can subtract the noise from your data. And we also did that step for our analyses for all of these gravimeters. And so we did the best we could, and the outcome was essentially this result. So omega GW is the energy density in frequency domain in gravitational waves. Of course, we don't really expect it to be at these values, especially today. I mean, advanced LIGO limits have gone down since then, by orders of magnitude. The pulsars at that time were already quite good. So the PTA searches, essentially, the pulsar timing arrays. So, but nonetheless, in the frequency band that we were able to access, which is millihertz, we were able to set with the observation of normal mode frequencies or amplitudes, essentially an upper limit on omega GW, which was weakly scientifically interesting simply because we got below the value 1. And 1, as you know, is kind of has a scientific meaning, because 1 is where if the total energy density were 1, then this is kind of distinguishing between different cosmological scenarios. But of course, there was no real scientific profit from that, from these studies. But what they did show was that we became much better than any laboratory experiment that was conducted on Earth or in space even before us. So we were better sometimes by 10 orders of magnitude compared to high precision experiments in the laboratories. And that gave us some confidence, and we started to look at this more carefully. We did follow-up studies also involving the seismometers that existed at some time on the moon. I mean, the seismometers are still there, but we use data from the 70s essentially to make correlations between the Apollo seismometers and then also between seismometers on the moon and seismometers on Earth. Because at these low frequencies, you can expect that gravitational wave signals would be correlated between the two. And so we tried all of this, and it's a bit complicated because, of course, Earth is rotating relative to the moon in a complicated way, if you want. So there's something that is called libation and different, components of the relative motion between the two that we all had to somehow include in our analysis to be able to describe the correlations between a seismometer that is on Earth and one that is on the moon. But we were able to set in a slightly higher band because the Apollo seismometers were not really sensitive at low frequencies. We were able to do analyses, and we were able to, improve previous upper limits by orders of magnitude, essentially using the moon seismometers. Okay, so that was the where we stopped for a long time. I mean, we had discussions at some point, can we do something better and what do we need? But we understood that, on Earth, you will not be able to do much better than we have demonstrated in these analyses. So for us, there was no obvious way to move forward with this idea. But then there was 2020, and there's Artemis, and there is the European Large Logistics Lander. There's a huge political and push for lunar exploration, and there is, of course, private interest at this point as well. As you might know, I mean, NASA specifically created the CLIPS program, which is based on a commercial payload service, essentially, that chooses companies to essentially deliver payload from Earth to the lunar surface. And the cost of these transports is much lower than what people knew from former times. By the way, I mean the US was really inactive since Apollo concerning the moon. So essentially, since that area, they didn't even have a robotic landing on the moon, no successful robotic landing on the moon since then. So even the US kind of starts to rediscover technologies. Of course, at the moment, mostly concentrated on Mars, but the moon, of course, will start to be of prime interest in the coming years. But in 2020, we had then independently, nobody initially knew of each other, the idea to submit lunar gravitational detector concepts. And there was a lunar gravitational-wave antenna. So I will say much more about this, of course, in this presentation. And you see that what it is essentially a kilometer-scale array of seismometers deployed somewhere on the moon. It's a quite specific location that we are targeting, but basically it depends on seismometers and an array of them being deployed. Then there is this lunar seismic and gravitational antenna, which was pushed mostly by Stavros Katsanevas, the EGO director, and it consists essentially of laser and of a laser interferometer, but for seismic strain measurements. So you do not have to, there are mirrors here at the ends, but you do not have to seismically isolate them. You can directly put these mirrors on the ground like you would with laser reflectors, And this is enough because you really want to measure the deformation of the ground produced by gravitational waves. And then there was the American team suggesting GLOC, which is essentially something like Virgo or LIGO on the moon. Now that is extremely challenging. I know I like to put them all in a timeline, one after the other, because first of yeah, I will explain this better. But the reason why we have an array here is because we believe that at some frequencies we might be limited by a seismic background on the moon. So meteoroid impacts, especially, but even moonquakes, can, in some sense, become, if they are just weak enough, there can be so many of them that they add up to a Gaussian background that you cannot really penetrate with your measurement, unless you have an ability to distinguish between seismic disturbances and gravitational wave signals. And this you can do with a seismic array. So we propose it for that reason. Now, I put LSGA, even though laser retroreflectors is nothing really new on the moon, I put this a little bit back in timeline simply because if they want to penetrate this seismic background, they will essentially need LGWA setups around each of these corners. So they would need 3 arrays, LGWA type arrays, around the corners to be able to also do this distinction between seismic background and gravitational wave signal. So for that reason, I see kind of this timeline forming, but for sure, if you talk to these people, they wouldn't necessarily agree with me. Anyway, so here's what we think what we can do. You have here the laser sensitivity curve, and here you have the Einstein telescope sensitivity curve. Of course, both at this point just targets. LISA is an approved mission. Einstein telescope is not yet an approved infrastructure, but we of course hope that it will be very soon. Now, I told you already that we leave this decihertz band, and people in the past proposed other types of detectors for that band, like the SIGO and Big Bang Observer, but these are technologically really, really challenging. I mean, we have no idea how to realize them. Now, given our current understanding of the response of the moon to gravitational waves, and given our estimate what sensitivity we can achieve to surface vibrations with our seismometers, we arrive at this sensitivity curve. So this is really beating LISA by a few orders of magnitude in above 0.1 hertz, which is very promising. And so that is really what tells me, okay, we have a shot at accessing this decihertz band. And then here at low frequencies, you can also see that we have this kind of peaks in the response or sensitivity, because we are here exploiting the resonant amplification of the moon to gravitational wave signals, because here you have the eigenmodes essentially of the vibration. Anyway, we are not competing really well with LISA, of course, at these frequencies, but I think even here we can have very interesting synergies together with LISA. But this here is really driving the main interest in lunar gravitational wave detection, and so in LGWA, I would say. So just to give you a little bit of information about the science case we expect, of course, when it comes to the lower frequencies, we know quite well that from LISA studies that we can potentially see binaries of supermassive or massive black holes. We can also see very well a certain range of what you might still call intermediate mass black hole binaries, with relatively high, wide horizon, up to almost redshift 6. So this is quite good for LGWA. Then again, okay, he's already indicated in some sense a little bit more. For example, we hope also to be able to see systems that start their in-spiral, that sweep through this band during their in-spiral, and their merger happening inside the band of terrestrial detectors. Now, this is very interesting. Even for intermediate mass black hole binaries, this is already getting interesting, because Einstein telescope will see them as well, even with relatively high mass of a few thousand solar masses. And the Einstein telescope, however, will only see the final part of it, the merger essentially, and combining it with estimates from LGWA in this band, obtained in this band or even lower, you would in a combined way be able to say much more about the sources, and also in terms of their sky location, for example. But of course, most interesting is that kind of scenario for Newton star binaries, because if you detect a Newton star binary in this band, this will be months to years before their merger. Observing it, up to a few hertz, at the very end, you will be able to give a very precise prediction when this merger is going to happen and at which sky location it will happen. So that is, of course, what people really would like for multi-messenger studies. So people would at some point observe the merger in gravitational waves with the ground-based detectors, and then everybody with EM facilities can already a day or so before it happens point to that source, which would, of course, be great. Now I should clarify this. You cannot do this with LISA. You cannot do a warning of a Newton star binary merger with LISA, simply because the masses are so low of Newton stars that the energy loss in gravitational waves is so modest at these LISA frequencies that when LISA observes the Newton star binary, it would take hundreds or thousands of years, depending on where the binary really is in frequency. It would take really a long time until it merges. Okay, so this is something that can be done with the decihertz detectors. And this is very important to understand. And this is always a little bit of confusion because, a few people would sometimes say sentences like, with LISA we can give warnings of Newton star binary mergers. That is completely inconceivable unless you are really lucky and you have a Newton star merger in your galaxy, which is of course not going to happen. But so just to say, this is a big advantage of LGWA. And here, a student from University of Columbia did some studies this summer, and we will not see a lot of Newton star binaries. The sensitivity is simply not, compared to ET, not good enough. I mean, we are landing here at maybe 10 to the 20 minus 21, 22 with the sensitivity. And ET, of course, goes, okay, this is characteristic strain. Let's say in most familiar units, this curve would go down to 10 to the minus 24, 25. So not in this plot here because it's a different kind of strain quantity. But in any case, we are about 2 to 3 orders of magnitude worse in sensitivity than ET. This is, of course, the reason why ET is seeing 100, potentially, several tens of thousands of Newton star mergers, or maybe even 100,000 Newton star mergers per year, while we with LGWA would be able to see maybe a handful per year. And also, a few tens maybe of black hole binaries per year. And if we see them, then however, we would be able to deliver very good sky location. So you are seeing here that we're talking about square degrees, up to 10 square degrees of sky location that we would be able to deliver. I think, of course, that would be extremely interesting. And one should still keep in mind, these are the ones that will merge, within 10 years after observation. So that is a little bit of a selection that we're doing. We might be able to see more of these systems, but then they are not going to merge within 10 years. And the other thing is that the lifetime of the experiment can easily be 10 years or even longer. So lunar gravitational-wave detections, and this is one of the big advantages, is can be realized with longer lifetime than LISA. Now, LISA has a nominal lifetime of 4 years, but people working for LISA would say, well, it's not inconceivable that LISA will last for 10 years even, or maybe even a little bit longer than that. In the end, there's a hard limit to the lifetime because there's a stability criterion of the orbits of the satellites. And so at some point you really lose sensitivity, but at some point also your laser light. So there is a certain hard limit to your lifetime. But on the moon, there is no really hard limit to your lifetime. But there's one challenge that, of course, you have to overcome, which I will explain later. So what I want to say is that, after 10 years, you would have 50 BNS detections maybe, or depends on, if it's 2 or 3 or 4 or 5, I don't know. But this is, of course, a little bit in the Poissonian noise. But let's say, 10 to 50 BNS detections in 10 years, or 20 to 50 would be possible. And I think this is a lot for people who really have the opportunity to study in detail this event in EM with a certain warning. I think these would all be very interesting studies. Okay. Then just very briefly about galactic binary. So from LISA, it is well known that there are many white dwarf binaries that you should expect to be detected. LISA will see tens of thousands, and many others adding up to an unresolvable foreground actually. But LGWA would still be able to see maybe hundreds to a few thousand of these white dwarf binaries. Now that is interesting, even if LISA exists, because the moon rotates a little bit faster once a month, right? Compared to the orbit of the LISA detector, which is like a yearly cycle. And so the detectors on the moon reorient within 28 months, while LISA reorients within a year. And this reorientation of a detector is a way to obtain information about the source direction, because you get a modulation of the amplitude that you see. And this modulation over time tells you where that source is located. And so that is what you can exploit. And so even if LGWA will just see, hundreds to a few thousand of these signals, it would be able to deliver better sky locations than LISA can, even though LISA has a little bit better SNR, of course, but still it would be able to deliver something interesting. And yeah, so there's some science to be done. Of course, the great hope would be that we are lucky enough within 10 or 20 years of LGWA lifetime, or whatever comes next on the moon after LGWA, that we will see a merger in our galaxy of two white dwarfs associated with a supernova type 1a, and then make the full multi-messenger study on the system. You have to be lucky, of course, because these mergers are not meant to happen very often. But if it happens, it would be a huge discovery, of course. And so LGWA or any decihertz detector would be instrumental to that, again, because the merger of white dwarf binaries happens in the decihertz band. Okay, so now let's go to a little bit to the concept, what we propose. So I already said, we say that we want to have an array of 4 seismometers on the moon. And the current idea is essentially to have, maybe the European Natural Logistics Lander bringing all of that in one landing to the moon, and then you have rovers who that would lay out the array for you. I'm already indicating here some other components. There's something deployed here with a red beam here. So I will explain in a bit what this means. Now, just to emphasize again, why the moon? I mean, people, because this is like a discussion that everybody is having with me about with whom I talk about this concept. So what about the seismic background on the moon? Is it quiet enough on the moon to be able to see gravitational waves? So I wanted to focus the discussion on this band, 0.1 hertz to 1 hertz. First of all, because that's a decihertz band, which is for us in many ways a really attractive target for lunar detectors. On the other hand, I can already tell you that for frequencies below 0.1 hertz, we do not expect a relevant seismic background. There's still a little bit of debate about this, but I think we are going to convince people quite clearly that there is no significant background below 0.1 hertz, or at least below several tens of millihertz. There will be no significant background for gravitational wave observations. So we can, in some sense, even focus on this band when we talk about seismic background. Now, here's the story. Here you have seismic spectra in units of meters per root hertz. So these are random spectra typically, but this histogram that you can see here, so blue means few support, red means a lot of support. So this kind of seismic noise is what you often observe, while this noise here is what you rarely observe. So these are all outliers, and they contain, for example, moonquakes, meteoroid impacts, even artificial impacts and whatnot. And here, the question is, what this is an observation of an Apollo seismometer on the moon. And so the question is, what is this red mode here, which is observed most of the time? It turns out this is the instrument noise of the Apollo seismometer. So this was Apollo 16, the instrument, and this instrument observed that spectrum almost all the time. And so since this is the instrument noise, what it means is most of the time the moon was so quiet that it was not even possible to observe a seismic disturbance. Now, just to put this in context, here you have the minimum noise that you can observe on Earth at any moment in time, anywhere, in a borehole, on Antarctica, anyway, anywhere. You will not be able to observe seismic disturbances below that curve. Okay, except for very rare statistical outliers. But let's say at a statistically significant level, you will never observe noise below that line. Now, that is already 3 orders of magnitude weaker at some frequency, 2 to 3 orders of magnitude weaker than the weakest level that you can observe on Earth. In reality, Earth is typically much louder than this level here, okay? And then we have models that predict that we expect a seismic backward on the moon, which is somewhere here at the lower end in this band. Now we are talking about what? 6 orders of magnitude and more, quieter on the moon than on Earth. Now that is a huge benefit. And I mean, that is exactly what enables gravitational wave detection for you to become interesting on the moon. Because of course the effort is enhanced because you have to go there, you have to deploy things. But the potential benefit is enormous on the moon. And these estimates that predict a seismic background here are even conservative if you want. It might well be that they are weaker than that, the actual background. This is something that we will have to assess with better models, but also with future measurements. So a huge gain here. Now, let me come back to this red line. This is a laser beam, and this is a solar power, these are solar cells, and they convert power into a laser beam, and this here shines onto some receiving panel to convert it back into electricity. Why that? Well, because we have to do something really extraordinary to see gravitational waves. You always have, this is always true. If you want to detect gravitational waves, you always have to do something extraordinary. It is never simple. So even in this very simple idea that you deploy a seismometer on the moon, you have to do something extraordinary. You have to use technology that is far beyond what people are used to. This is always what you have to do for gravitational wave detection. You have to go far beyond what people have done so far. And we believe that we can only do this if we have a cryogenic instrument that is for us something that operates at 4 Kelvin, for example. That allows us, for example, to make use of superconductor technologies, of very low noise electronic amplifiers, and so on and so forth, to read out very small vibrations produced by gravitational waves of the lunar surface, because these vibrations are truly tiny, of course. So you have to provide a concept that is convincing, that really people believe this can lead to gravitational wave detection. And we believe that we can do this only in a good way in what we, in these permanently shadowed regions. These are craters at the lunar south or north pole, which cast a permanent shadow on a certain region there. And in these regions, it can become continuously below 40 Kelvin. It can even be continuously below 30 Kelvin in some spots. This is extremely cold, but for us, it's a crucial advantage in many ways. But most importantly, because it allows us to use a technology that only has to get us from this 40 Kelvin down to 4 Kelvin. And it turns out that this technology is already available, and in a way that it doesn't produce vibrations in your environment, because anything that cools you down typically causes also vibration. But here, in this case, we believe that we have a concept that can get us to 4 Kelvin with a low vibration cooling system. And that is very important. So other advantages of this permanent shadow is that the sun in these areas where you have sunlight, the sun would lead to deformations of the sunlight, fluctuations in heat, changes in heat because there's a day-night cycle. All of that will produce excess ground motion in parts where you have sunlight. And all of this is avoided if you go into a permanent shadow. So there are several examples why this is good. But if you go into a permanent shadow, then you have to provide power to your experiment, which is a non-trivial problem. Now, here's the thing. If we had Apollo technology today available, then we could immediately, we developed the seismometer. We would say, okay, we demonstrated seismometer performance on Earth, so now let's get it to the moon. We would be done by 2035. The reason why we can maybe not promise really at this point a 2035 deployment as a possibility is mostly because we don't know how to achieve the capabilities of Apollo missions today. So Apollo had nuclear power devices for each of their seismometer deployments. And these used plutonium. Now, plutonium, they used there. No, it's not the only option, but it's the one favored by NASA. And plutonium is not really, people don't really like to work with plutonium today. I mean, it's of course a politically difficult issue. So plutonium, whether it will be an option in the future again, we don't know. But in some sense, for now, we kind of tend to exclude that option, nuclear power. Now, if we don't use nuclear power, then at the poles we have a second option, which is laser or microwave power beaming. So around these craters at the poles, you have a long sunlight illumination, like even at some points 80% and more. Okay, so if you put a solar panel here in these spots here, where you have a long sunshine illumination, then with some battery technology deployed here, you would be able probably to continuously power an experiment in the permanent shadow. All of this has been investigated for other missions already, so people are not unfamiliar with that idea. But this will take time for development, and I believe that this problem outlined on this slide will drive our timeline. It's not us developing a seismometer; it will be them, whoever that is, developing power systems for future lunar missions. And by the way, this kind of problem doesn't only exist for the permanent shadow. It exists with every experiment that you want to bring to the moon that is meant to survive more than a few months. Why? Because surviving 14 terrestrial days of lunar night, okay, one lunar night is 14 terrestrial days, surviving that much of a time without sunlight is not trivial. And so if you want to have a 10-year-long experiment on the moon, you always rely on something like this. There's no option, okay? In addition to this here, you could also have a satellite in orbit and you beam down the power to your permanent shadow, for example. That's another way to do it. But in any case, this is a problem that is really hard to solve, but has to be solved, not only for LGWA. I will skip this slide more or less. I mean, this is a little bit about information, how we will attempt to model the seismic background. We have a very good understanding of micrometeoroids and larger meteoroids and their rates and how they impact the lunar surface. From this, you can, with the response model, really say what the lunar, what the seismic background is going to be. And then once you have a better idea, you can think about noise cancellation techniques using the seismometers in the array to distinguish between seismic background and the gravitational wave signal. We intend to probe this technology. Oh, I see that I'm already at 45 almost, right? Or do I still have 5 minutes?
I was about to say that. Yeah, you have about 5 minutes.
Okay, good. Then what we can do is, because people say, okay, how do you know that the seismic array will work and be able to do this? So you can test this on Earth in a relevant environment. So it turns out that Mount Etna has geology which is quite similar to the lunar surface geology, which is the regolith, which is unconsolidated fallout from meteoroid impacts, essentially. And you have a similar condition here on Etna. So we are now working with LGWA essentially to look into seismic data from Etna. And if the setup was not perfect for us, we will be able to deploy instruments there to do dedicated studies. We also, need, together with the seismometer, that we are going to develop a test facility on Earth, which has to be really low noise as well. trying to emulate as much as possible the lunar environment, which is not perfectly possible on Earth because Earth is too noisy. But we will install a seismic isolation platform at LNGS and then test our instruments on this platform. We have to study a lot the physical environment of LGWA, not only in terms of the seismic environment, but even aspects like dust, like electromagnetic fluctuations and fields, charges, temperatures and thermal fluctuations, cosmic radiation. All of this can matter, and we have a lot of information already that we can still process for LGWA, but we have to add to this from future experiments. And here I just want to outline a little bit the technologies that we are going to need, and I assume that this is not even a full list, but I want to take the opportunity to point out that, and this is my last slide, to mention two future experiments on the moon, which will be very, very important for LGWA. First of all, there's a NASA CLIPS mission that was selected to be deployed in 2024, which is called Farsight Seismic Suit. And so essentially, you have heard for sure of the Mars Insight experiment. So there was a seismometer part of that, and the group that developed that seismometer had spares. And it turns out that with small modifications, you are able to use these spares on the moon. And so this is what they would do. They would bring a spare to the far side of the moon and deploy it there in 2024. And these are really good by today's standard. They are like at the best, sensitivity that you can do right now with, off the shelf, if you want, more or less. It's not really off the shelf technology. But anyway, and so this made it possible essentially to deploy within 2 years, because it was selected only now this year, and it will deploy like 2-3 years later. So it's a very short time scale, and this will of course give us a lot of more information about seismic disturbances on the moon. But this will be short-lived. So this is predicted to survive a few lunar nights, and then it will be off. The Lunar Geophysical Network is more ambitious. It's like $1 billion mission, which we expect, it's not selected yet, by the way, but people think that the deployment might happen early 2030s. And they are targeting a long-lived deployment, like 10 years maybe. And so this experiment has to solve the power issue as well. Probably in their case, it will be nuclear power devices. And so that is going to be very interesting. Of course, a lot of geophysical information coming out of this experiment. But for me, most interesting is what will be the solution that they will choose in the end to power the experiment for 10 years, because that is going to accelerate LGWA at this point. So I'm at least, interesting things coming up in the near future. And at this point, I want to stop. Thank you.
Thanks, Ian. Thanks for your nice talk. Time for questions. Okay, so I'll go first.
Yes.
So actually, I'm more than a curiosity, more a curiosity. So about the energy, which is something that you just mentioned. So the problem is more with the plutonium solution than with the nuclear solution, or it's the nuclear solution itself, which is kind of